Hello everyone, I'm Xianfeng Tang from Penn State. Today I'm going to introduce our KDD paper, Knowing Your Fate, Friendship, Action, and Temporal Explanations for User Engagement Prediction on Social Apps. This paper was done when I was an intern at Snapchat. Snapchat has millions of users and is still growing fast. However, our understanding for user engagement is still limited, as the first priority of most social apps is to attract and maintain a large user base. Understanding user engagement plays an important role for retaining and activating users. Here are some questions. Why a user is attracted by Snapchat? Will a user still be active after 1 week? To answer those similar questions, it is necessary to understand the engagement of users. To better understand user engagement, we began with the following 3 questions. What is user engagement? How to quantify the engagement of a user? What is the reason or cause of the engagement of a user? However, understanding user engagement is not an easy task, and there are 3 major challenges. First of all, as engagement objectives may differ across apps and even across features in one app, how to define the user engagement that can fit downstream applications at most is a question. Secondly, user historical data in social network apps are typically heterogeneous. A user can have friendship, actions, and user-to-user interactions. How to model those types of data together is another question. Finally, how to generate meaningful explanations for user engagement is a question. There are some existing approaches for similar problems. The first group focuses on returning of existing user, including churn rate prediction and lifespan analysis. Recently, more and more researchers try to predict user engagement directly. They use feature-based method, which predict user engagement based on features such as demographic information and user activities. State-of-the-art approach apply dynamic action graphs on users to predict their user engagement score. However, there are some limitations of existing approaches. First of all, they fail to model the friendship dependencies or ignore the user-to-user interactions when modeling user engagement. User-to-user interaction is an important characteristic of social network apps, and modeling them explicitly can contribute to the prediction or understanding of user engagement. The second limitation is that most existing work focuses on fixed engagement definitions, which is not flexible for different functions and different apps. Here we give an example. To measure the engagement with respect to the camera feature, we may choose the total time use of the different lens. This obviously is not a good measurement for user engagement on the Discover page or on the Friends page. The last limitation is that most recent methods focus on an accurate predicting of user engagement, but fail to answer why a user is engaged. People design black box deep learning models to do an accurate prediction. However, those deep learning models cannot answer why a user is engaged or not. To tackle those limitations, we propose a new framework to understand and predict user engagement in this paper. And we answer those 3 questions we propose as follows. We define user engagement using expectations of matrix of interest, which makes our definition flexible for different downstreaming applications. To predict the user engagement, we use an end-to-end deep learning framework that takes user historical data to predict his or her engagement score. Finally, to understand user engagement, we make the framework self-explainable and design 5 different types of explanations for user engagement. We then move on to the details. We first introduce some preliminaries, including time interval, friendship, user interaction, which describes the direct communication between friends, and user action, which characterize how users interact with different in-app functions. We further propose the dynamic user graph, which includes all those informations for each user. The graph structure of a dynamic user graph contains the social network of users that are related to the central user U. Node features describe the user actions of different users in this dynamic user graph, and edge features describe the user interactions. The user engagement score is defined using the expectation of matrix of interest. Our intuition is users that are more engaged should be more active and then contribute more to the app. Using the expectation of matrix ensures the flexibility of our definition, since the matrix can be selected according to different scenarios and different downstreaming tasks. As the matrices are changing over time, our definition makes sure the engagement score also has a temporal dynamicity. Meanwhile, using matrix of interest makes the definition of user engagement easy to understand and has a clear meaning. The formal definition is as follows. Example of the matrix can be session time or revenue from the advertisement clicks, and so on. We then introduce some user engagement explanations, which is expressed via different importance vectors. The first one is user action importance, which is defined for every user and every type of user action. It assigns a score for every action, which reflects its importance to the user engagement of the user. Second one is temporal importance. It can be treated as a time-enhanced version of user action importance, which assigns a score for every user action in every time interval that characterizes its contribution to the user engagement. The third one is friendship importance, which gives a score to every friend of the user, and the friends that contribute more to the user engagement should have a higher score. In addition to the explanation for every user, we also define two global importance vectors that is learned on the whole dataset. Those global explanations informs overall app-level user behaviors. We formulate the problem of explainable engagement prediction as follows. We aim to build a framework that can predict the engagement score with explanations based on the historical user graphs, and it can also generate global explanations for all the users. So let's move on to the details of our framework. We propose this framework to predict user engagement. Our framework mainly contains three types of modules, including friendship modules, temporal module, and attention mechanisms from the bottom to the top in the framework. Firstly, we use friendship modules to model the nonlinear social network correlations and user interactions from different user dynamic graphs. Next, we utilize the temporal module based on tensor-based LSTM to capture the temporal correlations from different graph representations. Finally, we deploy a mixture of attention mechanisms to predict the user engagement score and jointly derive the explanations. The friendship module contains two parts. First part uses a tensor GCN to learn specific information for each type of user actions from every neighborhood. The second part learns a neighborhood attention using user-to-user interactions and use the neighborhood attention as a weight to penalize the different representations from its neighborhood. The final graph representation is a weighted average result of node representations in this graph. The reason for learning a special neighborhood attention from user interactions is because we observed that most users only chat with less than 20% of friends, as shown on the right side. We select a city from Snapchat as an example. You can see most people only chat with a very few percentage of friends. Therefore, it is important to weight friends by their closeness, and the true closeness can be learned from the data. Next, we introduce the temporal module Similarly, it uses tensor LSTM, which captures the temporal dependencies and gets exclusive embedding vectors for each type of user actions. The temporal module takes the graph representations from friendship modules as input and generates output that preserves temporal dynamics. Here we show the formal definition of tensor LSTM. As we can see here, the tensor LSTM replaces the matrix multiplication with the tensor-based multiplication in the conventional LSTM equations. We then introduce three latent variables, ZA, ZJ, and ZI, which represent user action, temporal, and friendship to help understand the influence of user engagement score. Let's go back to the framework. At the bottom, we can see friendship modules aggregate node embeddings from every user in the dynamic user graph with the weights from friendship or neighborhood attentions. Next, temporal attentions from the temporal module is used to aggregate the output from TLSTM and learn the global representation that preserves the temporal dynamics. Next, an action attention is also derived using the representation vector that contains exclusive information for every user action. Finally, the user engagement is predicted using the combination of the distribution of every user actions. The individual user level or local level user engagement explanation are derived directly from the attention score we learned. Using attention as an explanation is widely used in the literature. Specifically, we use the friendship attention or neighborhood attention as the friendship importance for every user, which is dynamic over time and changing on different friends. Similarly, for temporal attention and user action attention, they are used as temporal importance and the user action importance. For the global level user engagement explanation, they are formulated as a vector and is learned jointly with the model parameters using EM algorithm. The loss function is given as follows. As we can see, the global importance serves as a constraint. The posterior is given as follows, and luckily we can find a closed form solution which reduces the computational cost of the framework. Now we introduce our experiments. We collect two datasets. They are from different cities, also from different continents. The historical data of all users living in each specific city is collected to formulate the dataset. To show the flexibility of our proposed framework, we then introduce two different definitions of user engagement. The first one uses user session time as the measurement of an engagement score, and the second one uses snap-related activities to compile a user engagement measurement. We compare with the following baselines, including linear regression, XGBoost, MLP, LSTM, GCN, and finally the state-of-the-art approach for user engagement prediction. First of all, we compare our proposed framework with all baselines on both region 1 and region 2 for both task 1 and task 2. We can see that our framework outperforms the baseline significantly. However, as we introduced before, we are not only interested in an accurate prediction of user engagement, but also want to know the reason of the user being engaged or not. To answer this question, we show the explanations from our framework. We begin with the global user action importance that's learned on the whole dataset. As we can see for task 1 and task 2, our framework derived different distributions on those user actions. For task 1, it infers past session time as the most important user action. And for task 2, we find that snap-related actions are the most important ones. Now let's take a look at individual user action importance. We randomly choose two users from the dataset. We plot their action importance and their label. The label is acquired from an internal tool. The story discover watcher means the user spend more time watching stories and watching discover videos, and the snapper means the user is more engaged on snap-related functions. Clearly, users with different dominating engagement behaviors exhibit different user action importance which are consistent with their behaviors. We then study the temporal importance derived from our framework. To this end, we plot the temporal importance scores of all user actions on both task 1 and task 2 in both region 1 and region 2. As we can see for task 1, our framework finds that session time is the most important user actions, and it finds the most recent time intervals plays more important roles in the prediction. For task 2, the framework derives that snap-related actions are more important than others. And in addition to this, we see some user actions has a temporal periodic importance score. For example, the chat send chat view story post has a higher importance in the same day of the week and same day of the previous week. Similarly, we also study the individual user level temporal importance. We randomly choose 2 users from the dataset and plot their temporal importance vectors. As we can see, the story discover watcher has more important scores distributed on public discovery view and the discovery view time user actions. But for the chatter, his chat send and chat view, so the chat-related user actions plays more important role than other user actions. Meanwhile, our framework can also find the importance of different time intervals. Next, we study the result of friendship importance. The result of 2 random users are shown on the right side. First, we plot the friendship importance distribution over time. As we can see clearly, different friends shows different importance score, and only a few friends can show relatively higher importance score. This also confirms that most users only chat or interact with very few friends, usually less than 20%. To further interpret those scores, we plot the importance of the highest user or friend and the lowest one. As we can see, highest important friend has a more similar user action to the center user, while the lowest one has a pretty different user action history. Finally, we compare explainability of our framework with XGBoost and LSTM. For XGBoost, the feature importance is used as an explanation. Since LSTM cannot derive explanation directly, we compute the temporal attention over its hidden output as an explanation. Clearly, those methods fail to learn a meaningful temporal importance across user actions or across time intervals. The XGBoost pays too much attention on the session time when doing the prediction task, while the LSTM has a much higher importance over recent time intervals. Now we have clear answers to those 3 questions. So thank you for listening. Our code is also available. Please follow the link on GitHub or scan the QR code on the right side for an easy access.